Rational functions. Here's the definition. We had mentioned it yesterday. We'll call it R. R of x is a rational function if it is the ratio of two polynomials. So an example, we'll put the examples in red. Example, R of x is equal to, and it's x squared, let's say minus 3x minus 40 all over x squared. Let's do minus 2x minus 8. Ratio of two quadratics is the ratio of two polynomials. This is a rational function. You know the deal. Domain, range. What happens to these on the whole real line as you move all the way to the left, all the way to the right? Those are all the things we want to talk about. There's an inordinate amount of time in pre-calculus where we talk about graphing these and all of these things, right? So we'll get into graphing that. I won't give you probably any assignments on graphing, but again, you know, my goal is we're going to obviously use some software here, and what I want to do is I want us to get to a place where, again, we know how to use the software, but we also know exactly why the software is telling us exactly what we see. Right? So that, again, we have a mastery of both of those domains. Okay? So let's go ahead and graph this. So Desmos, we're talking about x squared minus 3x minus 40. It's the ratio, so I'll put the fraction bar first, all over, I believe it was x squared minus 2x minus 8. 2x minus 8. Right? Lots of funky stuff going on here, right? And we want to break the whole thing down. So there's some stuff going on in terms of the axes. It hits the axis. Oh, let's get it all. This is what's great, right? So we've got to explain these things, which are not so hard to explain. Maybe explaining this thing, explaining that last one, is a pure calculus problem. Okay. So we will not be able to explain that this is a local minimum in this area. Of course, this is not an absolute minimum. For the people who are going to be watching the video, I'm talking about this point right here. This point right here is a local minimum. It's not the absolute minimum because all these points would go lower, obviously. But in this area, obviously, in this area right here, this is the smallest value. It's a local minimum. I will not be able to demonstrate that that is a local minimum in this context. Okay, but this is for sure calculus context where you'll be able to find that number for sure. Our investigation lies in being able to explain a lot of these properties, again, without looking at the graph. And therefore, when we do look at the graph, we'll be able to see why these things happen, right? Y equals 1, right? X equals, looks like, what is that? These are by 2's, right? So it looks like it's 4. And then it looks like x equals -2. Right? There's some things going on with all of those things. Okay. Okay, so let's start. We can start with, first of all, the domain. All right, so we talked about this earlier, and of course that's where we should always start, that the domain is a set of values that are allowable for you to plug into R. Here we're clearly dividing, and so we need to make sure that the denominator is not 0 in this case. So we're going to set the denominator equal to 0 and solve. So when investigating this, of course, we want to start with the domain. We're going to set x squared minus 2x minus 8 equal to 0 and solve for that. We are going to factor and find those values using the zero property law. Problems like this in investigating these things are often the longest and most tedious things, right? Because you want to find the domain, you want to find where it hits the x-axis, you want to find where it hits the y-axis, you want to find what happens near the places where it's not in the domain, you want to know what happens in the long run to the left and to the right. You just want to ask everything about this, and then you might want to try and figure out how to graph it, right? Now, this last part of trying to graph it is now becoming archaic because the technology has gotten to a place where we can get the graph pretty nicely, right? So I won't be asking you to graph one of these things, but again, I will be asking for you to know about what's going on about it, right? Which should allow you to graph it anyway. Factors of -8 that add up to -2 are -4 and +2. X minus 4 is equal to 0, x plus 2 is equal to 0, x is 4, and x is -2. The most basic part of a graph is knowing where the graph exists. And so wherever this graph exists, it should be skipping over -2 and skipping over 4. The domain is -infinity to -2, union with -2 to 4, union with 4 to infinity. And the graph verifies that. The graph correlates it. The range, again, is a calculus problem. It's hard to know what the range is. That's why the graph is useful, right? It looks like it's going to be, we'll be able to make some guesses about the range given all the other stuff we're about to do. Okay, so here's our first instance of where we're going to be looking at the graph, and now the question becomes, well, what's going to happen, you know, as you get closer to -2, and we should look at some values. This is also what's nice about the graph, right? So I can go here, and then I can do a table of values and say at -2, of course, we have some problems, right? So at -2, Desmos knows, the programmer, she decided to put in the word undefined for -2, and that's perfectly okay. Right, so we're not putting -2, we're not going to give it a value, and so it's not a real number, so let's leave it as undefined, right? But now it seems like that the closer we get to -2 on the graph, the more the graph seems to be doing something, right? And of course, I'm being biased about what closer means, because this is closer on the left, right? So I could be getting close on the right, of -2. Right, so let's do both. So at -2 is undefined. I'm going to take -2 out, and let me get on the right. Let me get on the left of -2. So 2.1, right? 2.01. These are numbers all on the left of -2, right? I should have put in -3, so at least it shows up. There's -3 right there, right? At -3, it's -3.14, and then I can get closer. -2.5, right? It becomes -8. So I should have put these in order, but it goes from -3.1 to -8 to -48 to -498. The closer I get to -2 on the left, the more negative it becomes. That thing is flying down to -infinity. So much so that we would say that the limit as x goes to -2 on the left is negative infinity. Limit from the left on this graph is negative infinity. The numbers get really, really negative the closer you get to -2 on the left. And so Weierstrass would say that the way that you would explain this to somebody is that they would say, well, no, I don't think it goes to negative infinity. And then of course they would say, you would say, well, wait, how far down do you think it goes? And then you would say, I don't think it goes under 5,000. And then you would say, you would just pick a value close enough to -2 on the left that goes below that. On the right, you would expect something similar would happen, right? That if I pick numbers closer and closer to -2 on the right, say for instance, -1.9, right? Or -1, -1 is 7.2, -1.5, right? So there it is, it's getting higher, right? It's that one. -1.75, it's a little bit higher. Where is that? That's that one, right? And that thing's going higher and higher on the left. I'm sorry, on the right. -1.9999, right? So on the right of -2, it gets higher and higher and higher. Right? So the calculus way of saying this is, again, that the limit from the right of the function, the limit from the right of -2 of the function is going to infinity. Okay. The way that we say this in pre-calculus is that as you approach these values, the graph gets more and more vertical. This is why we call these things vertical asymptotes. Right? So that line is going to be called a vertical asymptote. The line x equals -2 is called a vertical asymptote. The calculus remark is that we say that the limit as x tends to 2 from the right of f of x is, in this case, it was infinite, or the limit as x tends to 2 from the left of f of x, in this case, is negative infinity. That's the calculus way of saying that. So a vertical asymptote in the pre-calculus terms, we're using hand waving terminology, is that the graph gets vertical the closer you get to it. In calculus terms, it just means that the function is going higher, higher, higher. That means the function is going to infinity on one side or the other or both, or it's going to minus infinity on one side or the other or both. We got one more, it's at 4, right? So the vertical asymptote, what is it? It's a vertical asymptote is what object is it? Is it a number? Is it a function? It's a line. Okay, vertical asymptote is a line. The line x equals 4 is also a vertical asymptote. We'll take a look at the graph. We'll write this in calculus terms. We'll translate this. F as x approaches 4 on the right. So this is how it's going to appear in calculus. The limit is x goes to 4, and then they have a little plus sign here of the function, right? And so all we're asking is, what is happening to f when you look at values of x? Now we know there's a serious problem at 4. We know that it doesn't exist at 4. And so any questions about 4, you have to break up into how you're deciding to approach 4, whether it's from the left or the right. Okay, so I've decided to look at it at this moment from the right, right? And so looking at it from the right, you want to put in 4.1, 4.01, 4.0001, look at those values, and hopefully they're either going all the way up or all the way down. It's one or the other, right? So the answer to this is either positive infinity or negative infinity, right? And so of course what we're going to do at this level for the moment is look at the graph and see what it looks like, but then we're going to also think about, well, wait, how can we tell without looking at the graph whether this is plus infinity or minus infinity, right? And it's not that hard to actually tell. From the right, let's just go back home. Did we get rid of it? I guess we got rid of it. Let's put the function back in there. So I need to call it f of x equal to, and it was x squared. What was it? Minus 3x. Minus 3x. Thank you, brother. X squared minus 3x minus 40 all over x squared minus 2x minus 8. At 4, the limit from the right, negative infinity. Okay. Limit from the right, negative infinity. Okay. So on the right of the vertical asymptote, what is the graph doing? On the left of the vertical asymptote, the graph is positive infinity. Right. Questions there? So at a vertical asymptote, you're either going to get plus or minus infinity. And so when the way you can tell this without looking at the graph is that you simply need to check the sign of one value, right? If you put in 4.01 or even 4.1 or even 5 probably into this and check the sign, you'll see that you get a negative number. And it's very unlikely that this thing's going to jump up to positive infinity if at 5 it's already negative. Right? If you plug in 5, you see that it's negative, the thing's going to negative infinity. On the left-hand side of 4, if you plugged in 3, you're going to see that you get a positive number. That means on that side, you want a positive infinity. You don't have a choice. It's either plus or minus infinity. You just need to check the sign, right? And that's just by picking a value on the right or the left, depending upon which one you're asking. Any questions about vertical asymptotes? As you can see, they wreck the graph, right? And you might want to know which way you're going if you intend to graph it. In the graphing situation, you're also going to want to know these values. This is not so hard, right? So I want to know these 3 points. So I want to set, you want to know where it crosses the x-axis. That means you want to set the function equal to 0 and solve. The function is a fraction, and you want the fraction to be 0. The only way a fraction can be 0 is if the numerator is equal to 0, right? So you're going to set the numerator equal to 0 and solve. This we're experts at. So that is the wrong button to press. That. So to find the x and y intercepts, set the numerator equal to 0 and solve. We're talking about x squared minus 3x minus 40, and we're back to factor town. Factors of negative 40 that add up to negative 3 are negative 5, negative 8, and 5. Right? By the zero property law, we get that we set them each equal to 0, x is 8, or x is equal to negative 5. Those are the places where you cross the x-axis. The y-intercept, plug in 0, 4x, right? So you've got x squared minus 3x minus 40 all over x squared minus 2x minus 8, right? So we're just plugging in 0 there. You're going to get a very nice, let's just go ahead and enter down a little bit. You're going to get a very nice, where's this thing? Okay, it's 0 squared minus 3 times 0 minus 40 all over 0 squared minus 2 times 0 minus 8, negative 40 over negative 8. This crosses the x-axis at 5. I'm sorry, the y-axis at 5. And we're almost done. We're almost done in our ability to draw this thing, right? Why is that? Right. I know I have serious problems at -2. I know I have serious problems at 4. And whatever I'm about to draw, right, better get vertical around those places. Okay? I know that I'm also crossing the x-axis, where is it? At -5, so I'm crossing the x-axis here and here, -5 and 8. And I also know that I hit the y-axis at 5, right? So then, in a lot of ways, I simply need to now check the behavior at the asymptotes. Okay. In other words, I need to know whether, when I'm at 8, whether I'm rolling this way or am I rolling that way. When I'm at this point, I need to be approaching, moving to the right, this line like this or like this. When I'm here, I either need to be going up like this or down like this, right? The vertical asymptotes dictate what's about to happen. They're like attracting the function all the way up or all the way down, right? This is why you would imagine in physics that asymptotes, right, are the things that we use to model black holes, right? Because they just, when you look at 1 over x squared, you'll see it, or minus 1 over x squared, right? You'll see that it looks like something's just pulling everything into that, as we'll see. Okay. So then now we can do some checking, right? So if we do x squared minus 3x minus 40 all over x squared minus 2x minus 8, you know, we can just put in a few values, right? If we put in 5, right? So it's 0 here, right? If we put in 5, we're talking about 25 minus 15 minus 40, right? And then it's 25 minus 10 minus 8. That's a positive over a negative, which is negative. So at 5, it's negative. It's got to be doing like that. You start plugging in values. So at 5, so f of 5, whatever it is 25 minus 15 minus 40 over 25 minus 10 minus 8, right? Just to check this one, that looks like minus 30 over 7. Who cares? It's negative. Right? So that thing flies down to minus infinity. If you put in 3, right, you're going to get a positive, right? Like that, right? If you put in -1, you're gonna get, you would just check, you're gonna get a positive. If you put in -3, right, you're gonna get a negative, right? That's it. Okay. So that once you have the where you hit the axes, the asymptotes are such attractors of the graph that you almost get the graph almost determined for you, because everything has to fly up or fly down. The only thing that's left is how do we deal with all the way to the right and all the way to the left. Right. So again, all you need to do is check a few points and to see what it looks like. All right. All the way to the right and all the way to the left. And so the question now is, what is the end behavior? Right? And again, in calculus terms, it means what happens when x moves all the way to the right, or when x moves all the way to the left. And here we're about to fight again. Questions about anything before we do the end behavior? So we got the vertical asymptotes. The vertical asymptotes force the graph vertically, or up to infinity, or down to minus infinity. You just need to check the sign by picking values in the respective area. Okay. So now the only thing that asks is what happens when I leave the 8 and move all the way to the right, or if I leave the minus 5 and move all the way to the left. And so now we'll have a discussion again. Now when x is getting large, we need to have a discussion like we had last time about what really we need to be paying attention to. Right? I think I called that F. I may have called it R. So now, as x tends to infinity, x is getting large and large and large and large and large. Okay? So x at 100, x squared is 10,000. You just double the number of zeros. 10,000 minus 300 minus 40. When x is 1,000, x squared is 1,000,000 minus 3,000 minus 40. When we talk about big numbers in this country, right, and in the world, we usually use the largest units. You know, when we talk about the deficit, we don't say it's, you know, 7,482,743,276,476.26 27 cents. We don't do that, right? It's in the trillions, right? You pay attention to the largest terms, right? We want to do the same thing for this, right? And that we said yesterday in terms of end behavior that the thing we should be paying attention to in the numerator is x squared. X squared is the largest power. It determines the whole thing. And again, you see that at 1,000. At 1,000, we think 1,000 is big, but then when we square it, we're going to get 1,000,000, and it's 1,000,000 minus 3,000, right? The larger you make x, the larger the difference between x squared and 3x becomes. X squared should be the only thing we pay attention to in the numerator when x is large. That argument follows also for the denominator, that it's x squared that is also dominating the denominator. Again, when x is 1,000, you get 1,000,000. When x is 10,000, right, that has 4 zeros, and you square that, you now get 8 zeros. That's 100,000,000. When x is 10,000, this is 100,000,000, and that's just 20,000. This has no conversation to have with this. When x is getting huge, I should only be really paying attention to these two things. I'm going to show all this mathematically in a second. Okay? I should only be paying attention to these two things. Whatever this looks like in the long run is going to be dictated by the x squared in the numerator and the x squared in the denominator. But we know what x squared divided by x squared is. What is that? What's x squared divided by x squared? It's 1. It's 1. Right. So as x gets larger and larger, the more this graph should get closer and closer to 1. And that's precisely what's happening, right? So that if I do a table here, and I put in, oh, I guess I can do that. Let's put in a table for that, right? Or for f of x. Can I do that here? Or do I need to put it in? Oh, well, I can do this here, right? So then I can do what is f of 100, right? 0.98. What's f of 1,000? 0.998. 10,000, right? Let's break this thing right? It gives up. The programmer says, okay, look, it's 1, right? I don't have enough space, right? It's not 1. It's not 1. It's never 1. Okay? So I want to be clear about that, right? You get as close to 1 as you desire. We've broken Desmos to say, okay, I give up. It's 1, right? But it's never equal to 1. You can prove that it's never equal to 1. Well, obviously you can prove that these two are never the same. These two are never equal, right? Except for maybe 1 or 2 places. But when x is really large, they're never equal, right? So it can get as close to 1 as you like, right? Of course, nothing stops us from moving all the way to the left. So if I'm moving all the way to the left, I just need to put a minus sign there. And of course, that's getting closer and closer to 1 in a different way from above, right? But you can get as close to 1 as you want from above, right? So 1, and then it seems to go a little bit above 1 and come back down. That's interesting. Questions about that? So we can look on the left, go this way. So it looks like there might be a local maximum somewhere. I have no idea where that is. And then it comes back down. Or maybe that's an error in the programming, right? But it looked like as you go far enough, it goes above 1. Oh no, it doesn't. Okay, so it stays under 1, right? So it looked like we saw a number above 1, which would be a mistake, right? Which is something about the programming. Okay. So what is it that I just did, right? So you look at the 2 highest powers and you simply take the ratio of them. Find the 2 highest powers and take the ratio. And that's going to give you an idea of what the horizontal asymptote is. The horizontal asymptote, right? So just like I had the line, did I get rid of the line y equals 1? Is it still there? I didn't turn it off, did I? Maybe I did. Y equals 1. Right? So just as I had a vertical asymptote, the horizontal asymptote also has something to do with infinity, but in the inverse sense. Definition. A horizontal asymptote is a horizontal line the graph approaches all the way to the right or left. And the calculus way of saying it is that the limit y equals a is a, see, this is the calculus definition. Y equals a is a horizontal asymptote if the limit as x tends to infinity of f of x is a, or the limit as x tends to minus infinity of f of x is a. Right? So if you move all the way to the left, all the way to the right, you're just flattening out. So again, it's the inverse of the vertical asymptote. So instead of getting vertical as you approach a number, you get horizontal as you approach infinity. Yes, please.
So to find the horizontal asymptote, you just divide the 2 minus 2.
I was just about to summarize this. This is good. Thank you for your question. Yeah. So then the point is now that if I had this, right? So now if I change this to 8 over 2, all sorts of things change. Okay. I'm only interested in the horizontal asymptote for the moment. Right? We can get all those other numbers in all sorts of ways, right? So things have changed. But what happened to the horizontal asymptote? What do you think that number is approaching now? What is it? 4. Right? So it's 8 over 2. So when the powers are equal, you just take the ratio of the coefficients. When the powers are equal, you take the ratio of the coefficients. Right? So here, the degree of the numerator is 2, the degree of the denominator is 2, and so everything else doesn't matter, and so it's just 8 over 2. Let's demonstrate why that is. Horizontal asymptote for x squared minus 3x minus 40 over x squared minus 2x minus 8. Right, so I'm going to make a couple of remarks first that we looked at 1 over x yesterday, right? So here's some remarks or some recollections, right? That 1 over x tends to 0 as x tends to infinity, and 1 over x squared tends to 0 as x tends to infinity. And in general, 1 over any power of x that's positive tends to 0 as x tends to infinity. So that when you're looking at 1 over something that's getting really, really, really big, then the whole thing is really, really small. The reciprocal of something really large is something really small. The reciprocal of something really large is really small. The reciprocal of large numbers tends to 0. I have something really big, flip it, it's going to be really, the whole thing's going to be really. We're going to use that here for me to try and convince you that when x is large, that gets really close to 1. Okay. Here's the reasoning. I've got x squared minus 3x minus 40 all over x squared minus 2x minus 8. And now I'm going to do something to this. So some math magic is going to come in, and I don't know why I keep picking that green. I never like it. So then I'm going to divide the numerator and denominator by x squared. Now why am I going to do that? I'm going to do that because x squared had made the claim. X squared has said that it was the biggest thing around. X squared has said that you should only be paying attention to me, and everything in relation to it is going to vanish. Right? So if that's true, that means that if you divide by x squared, then x squared should in that way show its dominance over everything. Right? Let's see if that happens. So if I multiply everything by 1 over x squared, I get, and now I'm just going to distribute, then I'm going to get 1 minus 3 over x minus 40 over x squared, all over 1 minus 2 over x minus 8 over x squared. Just divide everything by x squared, please. Oh, I appreciate that. So if we want to, so I want to show that this is going to look a lot like 1 at the end, right? And the way that I demonstrate that is that you divide by the thing that is the highest power. And by dividing by the thing that's the highest power, then you get to see how each one of these things compares to the highest power. So dividing everything by x squared gets you this, right? How do I know I'm not dividing by 0 here? Right? Because x is getting larger and larger and larger, so I'm not dividing by 0. But that makes sense that, so I'm dividing by x squared because it's the highest power right here. So I'm just going to divide by the highest power.
It's going to give you, like, what's the result?
Right, so now that I have this, the question is, so now this is equal to this, okay? Now looking at it in this way, what happens to this when x is really large? What happens to that? Right. So 3 over x, when x is larger, gets really small. So that goes away. 40 over x squared, when x is really large, when x is 1,000, this is 40 divided by 1,000,000, which is really small. When x is really large, this is really small. And when x is really large, this is really small. The larger x gets, the smaller these things become, and they eventually, as x goes all the way down, go away. And you're left with 1 over 1, which is 1. And so that's the reasoning as to why this whole thing goes to 1. Because the largest power just wrecks everything else. Right? So this is our way of mathematically demonstrating that the largest power, that these things relative to the largest power mean nothing in the long run. And so then you would say that as x gets larger, this tends to 0, this tends to 0, this tends to 0, and this tends to 0 as x tends to infinity. And so the whole thing goes to 1 over 1, which is equal to 1. Y equals 1 is a horizontal asymptote. So you would divide by the highest power in the denominator. You would divide by the highest power in the denominator. Questions about that? So that is the only thing that we needed to end this discussion about graphing it. And so then it looks like now, oh, maybe it's on the same page. Is this page just long? No, I had it on a different page. But we were trying to graph this. The only thing that was left was this last line. This one. Y equals 1. I should use purple. And so now that's it. And that's a sketch of the whole graph. I'm going to talk about horizontal asymptotes in all the cases in just a second. Okay. But any questions about analyzing rational functions? That's the analysis you would do, again, in pre-calculus courses in high school and in college. You would go through this ad nauseum, just over and over and over again, 15 of these, where you would look at where it hits the x and y axis, set the denominator equal to 0, set the numerator equal to 0, define the intercepts. You would then look at what happens all the way to the right, all the way to the left. You would then try and figure out what happens at the asymptotes by picking values that are close on the left and the right to determine whether it's positive infinity or negative infinity, and then you would piece that all together to draw a graph like this. I wanted to do this once, right, for you together, and then yeah, there might be a few in the homework to do, right, but it's all of that stuff together. Okay. Let me finish the discussion about horizontal asymptotes. I've been biased in assuming that the powers would be the same. Maybe the powers are different. Let's do another one. Okay, so, and let me just talk about horizontal asymptotes for just a moment. So then, what if the powers are different? Asymptotes. Horizontal asymptotes. And so now if I have y equals 2x minus 3 over x squared minus 4x plus 11, right? The question is, I'm sorry, I should call that f. Let me call that f of x. Only because when I say the horizontal asymptote, I want to call that y equals. So I shouldn't use it. I shouldn't use y there. All right. So the question is, horizontal asymptote, what is it? Just to save us some time in myopen math, of course, when they ask for a horizontal asymptote, like for the last one, it was y equals 1, right? If myopen math or my math lab asks for the horizontal asymptote, if you put in 1, they're going to mark it wrong. 1 is not a line, right? Y equals 1 is a line. Right? So, yes, we're being anal, but that's true. Y equals 1 is the answer, not just 1, right? In this case, it's 0, and so it's because for the same argument, right, here, there's a fight. I want to know the horizontal asymptote. X is getting larger and larger and larger and larger, and so the question is, what's dominating here? And it's x squared. X squared is the largest power here. The street version is simply this. X squared is like, I'm the big dog here. I'm going to make the denominator way bigger than the numerator could ever catch up to. I'm a fraction and the denominator is way bigger. The denominator is going to be infinitely larger than the numerator. This whole thing goes to 0. The whole thing goes to 0 simply because x squared is the biggest thing here and there's nothing that can match it. Y equals 0 is the horizontal asymptote. Simply because this power is higher than this one. Okay. We'll talk about the math in just a second, but that's the quick, on the street version, that this is y equals 0 as a horizontal asymptote because this power is bigger. I'll demonstrate that in just a second. Go ahead.
The 2 has no effect on...
What 2? This 2?
Yeah.
Absolutely not, right? So again, this could be 3 trillion, right? And the reason why this works is because I don't care what happens early on. So early on, this might be larger. Actually, at 2, this becomes bigger. So at 1.3, this is bigger. 1.9, this is bigger, right? But after 2, and it doesn't matter when, but it's after 2, this thing starts to dominate this one, right? So this 2 has nothing to do with it. That could be any number you want. It's about the fact that I get to make x as large as I want, and I can make x large enough so that the 2 doesn't matter either, right? So mathematically, there's nothing different from what we had just done already. So the way that you show this mathematically is that you would divide the numerator and denominator by x squared, right? So this is 2x over x squared minus 3 over x squared all over 1 minus 4x over x squared plus 11 over x squared, right? And so x squared has now come to town and say, okay, you want to fight? Let's fight. Right? 2x over x squared is 2 over x, which is about to vanish. 3 over x squared never has a chance. 1 is going to hang out there, 4 over x, and then 11 over x squared, and now x is about to get huge. And as x gets larger, right, becomes 2 million, 8 trillion, 400 trillion to the 300 millionth power, right? 2 over that is going to start to fade away. 3 over x squared is going to fade away. So all these things go to 0. And you're left with 0 over 1, which is 0. Y equals 0 is the horizontal asymptote. And again, I don't even need to look at the graph to know that. It's just all reasoning it through. Right? So this is for sure an argument you'll make in calculus. By the time you get to calculus 2, you won't even have to show this stuff. You'll just be able to say it, right? That this goes to 0 as x goes to infinity, or that y equals 0 is a horizontal asymptote. All these arguments have been biased. All these arguments also work as x goes to minus infinity on both sides, right? There's no reason that these still become zeros as x gets really, really large. Who cares about the sign, right? It's still going to go to 0. And then finally, the last case is when the power is higher in the numerator. H of x is equal to 7x to the 4th minus 2x plus 1 over 6x squared plus 3. Here, there is no horizontal asymptote. You can show this in a couple of ways. But here, the street version, power here is higher. If these two are going to fight, x squared comes around and says, okay, you're moving all the way to the right, you're about to make me huge. And then x to the 4 says, but I'll be bigger. If a horizontal asymptote, if the street version is that the horizontal asymptote is a line that the graph levels out at, the graph is going to flatten out and calm down around this line. That certainly would not happen here, right? Because x to the 4th is getting bigger than x squared, and this thing's going to pull it up to infinity as you move all the way to the right. The other way to do this, of course, is to do what we did yesterday, is to go ahead and divide. When you divide, you will take this into this. X squared goes into x to the 4th, x squared times. This thing is going to be x squared plus a bunch of other stuff that will eventually go away, right? The remainder is going to vanish. And so this is going to look like x squared, and we know what x squared looks like. X squared does not have a horizontal asymptote. This looks like x squared. The way that you would show that, of course, is you would divide everything by x squared, the highest power in the denominator. I'll do that in just a second, and you'll see that this really just looks like 7 over 6 x squared. Then we'll summarize. The reason why this has no horizontal asymptote is because this, of course, is equal to 7x to the 4th over x squared minus 2x over x squared plus 1 over x squared over 6x squared over x squared plus 3 over x squared. Divide everything by the highest power in the denominator. You could take the time to divide everything by the highest power, period, and the whole thing, but it's easier to see if you just divide by the highest power in the denominator. This is equal to 7x squared minus 2 over x plus 1 over x squared over this 6 plus 3 over x squared. And when you start to think about what vanishes, again, these three things go away, being numbers that are divided by powers that are getting huge. But this thing here, as x gets large, this thing gets large, and the whole thing goes to infinity. The whole thing goes to infinity. So this thing tends to infinity as x tends to infinity. And infinity is not a number, and therefore there is no horizontal asymptote. We'll summarize. Street version, you have the ratio of two polynomials. If the powers are the same in the numerator and denominator, then you just take the ratio of the coefficients. If the power is higher in the denominator, it's y equals 0. If the power is higher in the numerator, there is no horizontal asymptote. I'll take questions. Now, I will be different from my colleagues, and I'll write that down. But you should have written that down, right? For the future, for the people who are not going to want to do anything other than hand and wave. We'll summarize. Horizontal asymptotes. Let f of x be equal to p of x over q of x, where p and q are polynomials of degree n and m. So n is the highest power in the numerator, and m is the highest power in the denominator. 1. If n is equal to m, then y equal to a over b is the horizontal asymptote. Where a is the coefficient of the leading term of p, and b is the leading coefficient of the leading term of q. It's just a over b. If the higher power is in the denominator, then y equals 0 is the horizontal asymptote. 3, if the higher power is in the numerator, then there is no horizontal asymptote. We'll drill on this and then we'll move on. Pretty straightforward problem on the test next week will be one of these. Find the horizontal asymptotes. Mojang is a great grader. I think she was nicer than I would have been in some places, particularly number 1. Number 1 on the test next week is define what it means to be a function, and I'll instruct her to make sure she's giving 0 partial credit for that. Right, so I've given you an answer to what I want it to be. Some people wrote some things that were not that. Right, so that is the fundamental thing about this class. If the class is about functions, if you're going to define what a function is, make sure you say that it relates 2 sets with the property that for each x there's how many y's? 1 and only 1. 1 and only 1. If you don't say that, 0 credit. 0 credit. Okay, so she was nice and gave +7s, and so people from past SAMs would be livid. They would be mad at you all for getting +7 for that. There is no +7. It's either 0 or 9 for that, right? So we'll talk about that again next Thursday about exactly what I want for that. And people didn't write that, but they wrote the essential elements. 2 sets, you assign 1 element of 1 to 1 and only 1 element in the other one, and that's perfect, right? So there's some people who wrote something that I did not write, and she marked it perfectly, and that was perfect, okay? But just make sure that you get that right, okay? Here I'll ask for find the horizontal asymptotes. You might expect that I would give you 3 of these problems. For instance, I would say, what's the horizontal asymptote for, or I would say find the horizontal asymptotes if they exist, right? I want to be fair, right? If they exist. So A would be something like 3x squared minus 7x plus 2 over 5x squared plus 2x plus 9. B would be g of x is equal to 6x to the 7th minus 14x plus 1 over 97x to the 10th plus x to the 3rd minus 2. And then C would be h of x is equal to 17x to the 9th plus 3 over 14x plus 15. And find the horizontal asymptotes if they exist. Yes? Oh, thank you. Maybe I'll decrease the view to 75. I was already on 75. Let's try 50. Okay, so then, is that good? Is that where you, okay, great. So, yeah. We're looking for a line. The answers to these, A, B, and C, are y equals, y equals, y equals. Okay. A, y equals 3 over 5. Questions? In A, the powers are equal. Take the ratio of the coefficients of those powers. B, y equals 0. Highest power, the degree of the denominator is 10, the degree of the numerator is 7. 10 is more than 7, 0. C? No horizontal asymptote. Good. Questions about any of that? All right, let's try and hit the homework, see what they're going to ask us. Oh, I'm sorry. Does anyone still need this up? Okay. Open math. videos for all of that right here if you like. See if there's anything we could have left out. Okay, great. So this function, it's all there for us. Here, this one's got us doing some factoring that's on a slightly higher level. We're not afraid of that. Here for the vertical asymptote is a line, so they've already given you the x equals part, which is nice, so you don't need to write x equals, so you just need to separate with a comma. The y-intercept is what happens when you plug in 0 for x, right? So then 3 times 0 squared minus 7 times 0 minus 6 all over 2 times 0 squared plus 1 times 0 minus 3, negative 6 over negative 3. Again, I think they want the point, right? That's 2. It's 0, comma 2. Plugging in 0 for x, getting the y coordinate. The x-intercepts we talked about setting the numerator equal to 0 and solving. So we're talking about 3x squared minus 7x minus 6 is equal to 0. This requires a little bit of thought how we're going to get a minus 7 in the middle. 3 is prime, so that has to be 3. That has to be x. And it looks like if I multiply 3 times one of the 3's here, that would give me a negative 9, and then I can add 2 to make it negative 7. That's not trivial at all. So factoring the numerator like that, right? So 3x here, 1 here, you need to put the factors of 6 here or here so that you get a minus 7 in the middle when you FOIL. Setting them each equal to 0, 3x plus 2 equals 0, x minus 3 is equal to 0. We're talking about negative 2/3 or 3, and it looks like we're going to be separating the points with a comma. Right, so it looks like this one we actually might want to put in and see if that's true. Has anyone tested this yet? We'll see if that's how you enter it in. And in vertical asymptotes, we need to set the denominator equal to 0. More funky factoring. 2x squared plus x minus 3 is equal to 0. Looks like I'm going to need to get a 1 in the middle. Again, 2 is prime, so it's 2 and 1. 3 is also prime, so I need to put the 3 here or here. And it looks like if I do a plus 3 and a minus 1, that'll give me a plus 1 in the middle. And you can verify that by foiling, right? So then 2x plus 3 is equal to 0, x minus 1 is equal to 0, x equals minus 3 over 2, and x equals 1 are vertical asymptotes, and we'll separate those with a comma 2. It looks like here you would put minus 3 over 2, comma 1. Here we're just checking whether the programmer likes that. Negative 3 over 2. So it says enter a point, 0, comma 2. Here we're entering negative 2/3, comma 0, 0, and then comma. What was the other one? 3, comma 0. Let's see if it likes this. Okay, and then negative 3/2, comma, was it just 1? 1. Let's see if it likes that. Okay. Yeah, that's exactly what it wants. Questions about that? Determine the long run behavior, right? So what happens all the way to the left, all the way to the right. What are you really asking for? Say it again. The horizontal asymptote, that's right. X squared plus 1 over x squared plus 2, y equals 1. Powers are the same, coefficients 1 over 1. Power is higher in the denominator, y equals 0. Power is higher in the numerator, no horizontal asymptote. Questions? Same thing, find a horizontal asymptote. The whole game. The whole game. Let's go ahead and work on this one. Answer this question. Exercise in factoring. This is everything. This is about as bad as it gets. Yeah. On the test, I might give extra credit for trying to graph it, right? So I'm going to give one obviously like this, and I'm going to say for extra credit graph it, because then that requires that you actually figure out what happens at the asymptotes, right? I might make the factoring slightly easier. I don't really have to, but the reason I would make it easier is because it's easier to check the asymptotes around, 1 and 3 instead of checking at a fraction, right? So just to make that part easier. To make them whole numbers instead. We're going to practice the way we intend to perform. Oh my goodness, I love this class. Oh my goodness. Funky y-intercept, right? Plug in 0, negative 15 over 4. Are we experts at factoring, or it just takes a little bit of time? A little bit of time, yeah. Right, 2x. The programmer seems to like prime numbers for the factors, for the coefficient of x squared, which of course is super helpful. We're talking about 3 or 5. I need to get an 11. 2 times 3 is 6, plus 5 is 11. 2 times 3 is 6, plus 5 gives you the 11 in the middle. Right. Negative 5 over 2, negative 3. Vertical asymptotes, set the denominator equal to 0 and solve. Right. It's the factoring part that really is the only part I'm worried about. Right? Everything else is actually something we can grapple and deal with and understand intuitively. It's like, yo, can you just factor this, right? 3x, x, looks like that minus 4 is there, the 1 is there. If you need a factoring crash course, we can do that for sure. X equals 4 over 3, x equals negative 1. Right. For the vertical asymptotes. Set the denominator equal to 0 and solve. And of course, the powers are the same, so it's y equals, it's just 2 over 3. They already gave you the y equals. Questions there? So street version again, plug in 0 for x for A, set the numerator equal to 0 for B, set the denominator equal to 0 for 3. Oh, let me ask you about methodology. So what I did today, right, and what I've been doing is that I'll come in and give you the whole overview, and then we'll go through and murder the homework. Do you prefer that if I just go through each one of the problems and then talk about it as we go? Or is there a preference? Do you care? Doesn't matter? Okay. So from the mathematician's perspective, it's just like, let me just tell you everything, and then we can just do the homework after talking about everything, right? If you do it per problem, then it feels disjointed. It's just like we're serving the homework when we should be serving the whole big idea, right? That's the point. So I just wanted to make mention of that. What happens, though, the downside is, though, that the whole story may be so big, we may not be able to get through all the homework, but at least we've talked about every topic in it, right? So let us see, given the time, let us see if there's anything in here that we have not talked about that needs to be discussed. Oh, let's write one. Okay, so now we need to write one. So these have often presented people with a problem. So let's go backwards. So I'm going to give you the information about this thing. And that should be all that we need. I'm going to tell you about the vertical asymptotes. I'm going to tell you about the x-intercepts. I'm going to tell you about the y-intercept. And then tell me what function I'm talking about. Okay. So street version, we know the street versions, that the vertical asymptotes are about the denominator, right? The x-intercepts are about the numerator. And then there's going to be some constant in front to make sure that I need to hit, when I plug in 0, I should get 2. Okay. And that should tell me everything. Okay. That one of the big discoveries that we decided, that Amelia made clear yesterday or the day before, was that polynomials are just the product of linear factors. They're just the product of linear factors. And so in this, when it says that the vertical asymptotes are 1 and -4, it's trying to tell us about the linear factors in the denominator. It's x minus 1 times x plus 4. Those are the factors that have to be in the denominator in order for me to have a problem there, right? If there's a vertical asymptote at 1, that means that when I plug in 1, I'm going to be dividing by 0. So that means that the denominator should have x minus 1 in it. If I plug in -4, I should have a problem, right? Go ahead.
Since it doesn't say the horizontal asymptotes,
It doesn't.
We could assume that the top part has a higher degree.
Or it could be the same. It could be the same. And because they say nothing about the horizontal asymptote, we can make it whatever we want. Yeah. I prefer to make it the same. Yeah. Because then that doesn't hurt. Right? The x-intercepts, it needs to hit at -1 and -3. What are the two linear factors in the numerator? X plus 1, x plus 3, for sure. Right. And that would all be good, and we will put that in, except we need to satisfy one more condition, and that is that when I put in 0, I need to get 2. Right, and this is where I start to lose people, but I'm not going to lose any of you here, right? So this means we're almost there. This is almost a function, right? But I need one more little number here, a, that I'm going to put in to make sure I satisfy that when I plug in 0, I get 2. I need to find out what a is, so that when y becomes 2 and x becomes 0, everything works out, right? So now I need to get 2 equals the a I don't know yet, times 0 plus 1, 0 plus 3, all over 0 minus 1, 0 plus 4. I'm going to take any questions about that. I have one more parameter that I need to solve for, and that's a. So 2 equals, that's 3a over 4. A is -8 over 3, and it's over. Okay? That's just one last thing I needed to satisfy. The answer is y equals -8 times x plus 1, x plus 3, all over 3 times x minus 1 times x plus 4. right? The 8 goes in the numerator, 3 goes in the denominator.
Would the computer be okay with just writing that?
Oh, we're about to find out, aren't we? Yeah, we're about to put that in and see if it likes it. But I'm going to take any questions about this. See if it likes it. I'm going to double check my math. That looks okay, right? -4, 3/4, yeah. All right, let's see if it likes it. All right, now putting this in is a monster too. You need parentheses. X plus 1, X plus 3. All right, so I have this first set of parentheses simply to encapsulate the entire numerator, right? So then I'll close this off to mean I want that whole numerator and then divided by, so that the computer knows to divide the whole numerator by that, right? So that's why I had those set of parentheses on the outside, and then I need a new set, and that's 3 parentheses, and it was x minus 1, x plus 4. It doesn't like it. I need one more to close off the denominator. See if it likes it. So I'm good about everything except for this -8/3. Let's see if it likes it. It does. Questions?
So you don't alter, like, you don't make it into a...
You don't FOIL it?
Yeah.
You can if you want, but it's clear that, yeah, and again, the grader would love to probably just see this. Because then if you see this, it's obvious that you know, like, it's just so clear, right? It only makes it harder for the grader if you write it in FOIL form, because we need to make sure that you FOIL correctly, and like you're making us grade more than we need to if you do anything more than that. Right. 6, same thing, roughly. Let's go ahead and they've added one extra condition that's different from the other one, so it's worth talking about. Horizontal asymptote. All right, give it a try. Get me to the answer. We're almost there. It looks like that you are going to have this a in front again, but you don't need to plug in 0. You just need to make sure that the ratio of the coefficients is 8. It's a rational function, so I need a fraction bar. Denominator, numerator. Looks like we got an x plus 4 there, an x plus 5 there. Vertical asymptote, so the street version is that the vertical asymptotes are about the denominator. The x-intercepts are about the numerator, right? X minus 2, x minus 4. They didn't give me a point. They told me that y equals 8 needs to be the long run thing. So here's f of x equals that. The degree of the numerator is, well, what is it? What's the degree of the numerator? What, the degree is a number, right? 2. Excellent. The degree is 2 in the numerator, and in the denominator is also 2. So the degrees are the same. So right now, right with what I have right now, what is the horizontal asymptote?
1.
It's 1, right? So the horizontal asymptote for this is 1, and I want it to be 8. What should I put here?
16.
Or 8. Yeah, 8 also works. I wonder what they would do if I put 16 over 2. I wonder what the programmers decided, but 8 works as well. Okay. 32 over 4, whatever you like, right? Yeah. Questions there? You want to put that in? Oh, you want to try? Ah, see, I know that you're a computer programmer now. Yeah, you just want to see. All right, so you're going to make me put this thing in parentheses 16, parentheses x minus 2, x minus 4, divided by x plus 4, x plus 5, and you put a 2 there, right? You want a 2 there? Likes it. Good. Good. No, I know. The programmer has done a fantastic job of de-emphasizing simplification. All right, let's do a quick scan, see if there's anything crazy. Okay, those would be fun. So write that equation. So yeah, good. This is where we start tomorrow. So we'll finish this assignment working together. Yeah, great. That'll be a lot of fun doing that stuff. Okay, so we'll end there. Tomorrow we'll finish this assignment, and then we'll finish this chapter, and then we'll move on to exponentials.